which is not due until the 25th, correct?
Yeah, it's the Monday after spring break.
Yeah, the 25th. So you'll have, so you'll have 23 weeks to work on it? I should have you do it by next week.
The take home?
Sure.
Did you wear black, assuming the role?
Oh, wow.
The bearer of bad news.
Brushing your
Crafting how to make your life more miserable than already is. Okay, then. Okay, then I've made my mind up. We definitely will have a Manova homework then. Okay, then we will do. So I was equivocating on that if I made you do the take home next week, but I'll give it to you 3 weeks. You'll find the take home is smaller than the other classes. There's not as much of a take home. Yeah, it's only 3 questions.
Let's do the 25th.
What's that?
Let's do the 25th.
Yeah, 25th, and then next week will be the Manova homework.
3 multiple choice questions.
No, no, not quite. But there are multiple questions embedded within each of them.
Great.
Right, the same. Okay, everybody, yes.
Do you think on break you could translate some of your notes? Only because I haven't quite mastered reading it
You
yet.
can make a game of it.
Yeah,
Like charades.
it's already 9:02 and you're busting my chops already. Yes, I know. Every weekend when I start creating the homeworks, I say, okay, I'm going to make my handwriting legible, and it just,
Aw,
by
you
about
do.
the third consonant, it just doesn't work out.
You can hire a translator and just
The
dictate.
smiley faces, I understand.
Yeah, I don't do emoto icons. It's just not the smiley face. That's just not my thing. So okay, yes, I'll be happy to translate my comments at the break.
Thank you.
It's a compliment because we want your feedback.
That's
I
right.
know, and I love giving feedback. So I always have comments. In fact, I have lots of comments, but it's just.
You should start doing like video diaries to go, as you read it, record it, and just give that to us.
God, that'd be great.
Wouldn't
Because
it?
some people say, Dylan, can you start typing out your stuff? I go, I don't have time to start typing out.
We should come up with a way you can just send us audio clips of, as you're reading, you say, okay, this looks good.
You can do that on your
But
smartphone.
then does that, okay, just audio, I was going to think I don't want the visual thing.
No, you don't have to type it. Just get audio.
I have really bad, right? Oh, God. So, one thing I do want to show you, briefly, and I don't know how good this technique is, everybody, so I have to learn a little bit more about this, but I'm on a project as of last week, and I hadn't heard of segmented regression. I've never heard of segmented regression, but I've done piecewise regression. Let's say you have time 1 to time 20. Let's say you have 20 measures of job satisfaction over time. Okay, let's just pretend, maybe it's weekly measures. Everybody with me? Weekly measures of job satisfaction. Let's just do the mean. And obviously, one thing you want to look at is whenever you have this many measures over time, you probably were interested in looking at what? 20 weeks of data of job satisfaction. What are you ultimately looking at? What's the overriding research question given the design?
Reliability?
Is there a change over time?
Change over time. Right? You want to look at change. What if I did, I'm going to put I for intervention at time 11. Let's say you did some type of intervention right here. What might help increase job sat? That'd be a major intervention. You guys are all future
Flex
IO
time.
psychologists. What's that?
Flex time.
Okay. It's been in the news a little lately, hasn't it?
Yeah, yeah.
Well, that's from working at home. Flex time's different.
Okay, right, telecommuting.
Yeah.
Right, fine. Telecommuting sure has been, boy, that Yahoo really has caused a lot of.
Did you see how she figured it out, though? She went back to the data to see how often the employees at home were actually checking into the system and
Slackers.
all that kind of stuff. So she's very, very data-driven. I thought you would like that part.
Yeah, interesting.
And she went back to see how much work they were actually accomplishing from home and was not happy with it. That
No
was the
kidding.
cause. That's
Really?
one. There's some speculation that was really the cause for the change.
Okay. Okay, then you know what? Let's get rid of flex time. Let's get rid of telecommuting at this point. Let's be Yahoo and get rid of it. So let's look at job satisfaction. Any differences in the slopes? Do the slopes look similar or a little bit different? A little different, a little steeper there. Do the intercepts look a little bit different? So you can look at what's called level and trend. This is called, how many people have ever heard the term an interrupted time series? This is called an interrupted time series. If you take a research methods class, and you guys had research, then you would have gone over these types of designs. If you had Shadish's book, Cook and Campbell, you would have gone over interrupted time series. This is especially nice for short, what's called a short time series. There's only 20 measures over time. This is called a short time series. So here, essentially, when I've analyzed this type of data, you have to use an autoregressive type of model. Autoregressive, remember we talked about autocorrelation? What does autocorrelation mean again in time-based studies?
Measures closer in time will be
Well, more correlated. And is that going to maybe happen with job satisfaction? We absolutely. Now, one statistical tool I've used, and not in SPSS Plus, is this thing called piecewise regression. Piecewise regression literally fits a separate slope for each of these points. And you could have a third point, right? I mean, you could have what's called a cut point or a threshold. So here, this article is called Segmented Regression Analysis of Interrupted Time Series in Medication Use Research. And I have to read more about this because it looks like they just do two separate regressions. And they code. They code pre-intervention, like a dummy code for one, and they get the data for here, the data for there, and do a basic regression analysis with both segments. And what I need to read more about is how are they taking into control, how are they taking into account autocorrelation? Because I understand statistically this would be very easy to do. It's just a regression and you code for it. But I'm curious as to how they take into account the autocorrelation of t and t minus 1, right? Time 3 and time 2, etc. So it's interesting, but I just want to show this to you. If you're reading a time-based study and maybe not having to learn the complexities of time series analysis. And time series is complex. There's just a whole new vocabulary and statistical tools associated with real-time series. But here it looks like this is in the Journal of Clinical Pharmacy and Therapeutics. And that segmented regression analysis, or what I used to call piecewise. I've done piecewise regression before. When we actually, it was a study done looking at risk and the stock market after Obama was elected. And we actually did have many measures over time. So this is just something I just wanted to show you, everybody, called segmented regression analysis.
For that, the intervention, what if you had an intervention where the change maybe didn't occur right away? Would that affect the outcome?
What do you mean the change? Because the intervention happened, but the
Well, I mean,
change
like
made-
the change that
the actual,
occurs in
yeah,
intervention,
that's why Shadish's Cook and Campbell classic book on quasi-experimental studies, they talk about abrupt versus delayed change.
Mhm.
The intervention still happened at that time, and it may not happen. You may find very well that you get something like this. That may not happen until week 14 or 15. Don't some of these psychotropics, the SSRIs, take a few weeks to get going in your system?
Yeah.
I'm not a neurologist, so I don't know, but don't they take like 2 or 3 weeks? If you start on Prozac or one of the
Yeah.
SSRIs, it takes like
To
3.
level out in the bloodstream?
Yeah, to
Yeah.
start taking effect.
Yeah, to start taking effect, and then it takes even longer to level out.
To level out. So if I took the Beck depression inventory every week, is there a chance, I think it is Zach's comment, that maybe I wouldn't see much of a change in depression, the 2, 3,
Right.
4, 5 days? In fact, it might be 3 weeks till I start seeing. So yeah, so you can actually examine that visually. It would still be the same analysis though. But that's why when we talk about, that's why there's a heavily visual part of short time series, is you may want to talk, does the change look delayed or what's called abrupt?
So visual inspection would be a big part of
Initially,
it.
especially short time series.
Okay.
Yeah, absolutely. And you know, it'd be interesting, now that I'm thinking about this, add a third, right? Do a line there, do a line there, do a line there, do 3 of these. If you think that, well, I know that interventions for telecommuting, intervention for depression doesn't happen until 3 weeks, I'm going to put PI, means post-intervention. That could be another cut point. and you'll do 3 of these. You'll do 3 segmented regressions. You'll dummy code for each of these, and then do that. I've done this in M+, with piecewise, what's called piecewise regression. So that might be something. If you have pretty good idea, Zach, and you think some of this stuff has a delayed impact, which many interventions do, then that would be a consideration. So I just thought I'd share about another statistical tool that you can use for these time-based studies. It looks like the regression is really easy to run. I need to read more of it to see how it takes that into account. Because it doesn't. A regression wouldn't take that into account. This violation of independence, which we've discussed as one of the assumptions already in Chapter 6. Okay. So that being said, everybody, we discussed independence already. We've discussed univariate and multivariate normality. And now you guys all know how to use the macro, right? Looks like all of you ran it correctly. You knew how to run it, so that'll be part of your take-home. And now, even though the book says there's no multivariate normality option in SPSS, there is now, because now you know the macro. And I would highly encourage you to use it actively in your research, especially focusing on the multivariate test with normality. As I also told you, I remember I told you last week that I did interact with Larry DiCarlo, and I said, what if one of the tests is kurtosis significant, the other aren't? He tends to use the Mardias, but he said that they are sensitive to certain levels of kurtosis. And what that means is, even the Shapiro-Wilk and the Kolmogorov-Smirnov, sometimes they're sensitive to certain parts of the tails. I've noticed there are some statistical papers that show some of them are a little more sensitive to the tails than others. That's why we're using basically the Shapiro-Wilk for the univariate normality. That seems to have the best properties. So we've discussed normality, univariate. We discussed briefly transformations. Again, some people, when they see transformations, they start thinking that you're doing what?
Manipulation.
Yeah, playing fast and loose with your data. All it is meeting the assumptions. So how's this look, everybody, for cost adjusted for inflation? Is this pretty severely? Is that a little bit better? True, there's still the outsides. When you do a logarithmic transformation, sometimes it can actually reverse things. So you may try a square root transform. All we're doing is, yes, the data doesn't make sense in terms of its descriptives anymore. Because here we're saying the average cost is about $3,000, and now we're saying it's 3.97. Can you imagine getting a bill from the hospital for $3.97?
Yes.
Well, yeah, you may, but I mean, for extensive services, though. But yeah, you will.
We gave you half a Band-Aid.
Right. You're right. Oh yeah, like a Tylenol is, well, I think $10, $12 or something like that. Yeah. So that being said, everybody, I have found, especially with financial data, these transformations work really well. I've analyzed lots of financial data for hospitals, and I found it really does a nice job of normalizing the distribution. I'll tell you what rarely gets help with transformations. A 1 to 5 point ordinal scale, item. It's not really, when you have you know what I mean by an item, a single item, it's usually not going to help. And you are going to get sometimes floor and ceiling effects with individual items. I really enjoy my work. I don't like my work. You may get a lot of people that either strongly agree or strongly disagree. So I have found with ordinal items, not the scales, which is an aggregate of multiple items, but the actual individual items all rarely are helped by transformations. What else is not helped? Have fun with this one. Yes, exactly. Have fun transforming that one. What are you going to do? What are you going to do? I mean, a log transform's not going to do it. A square root's not going to do it. An inverse isn't going to do it. An arcsine transformation. What does this tell me when you get a bimodal? What does it tell you about the data? Let's say the item is, I really enjoy my job.
It's like you have a total floor and ceiling effect.
Okay, which means what?
Which means everybody loves it or everybody hates it.
Which means you have,
Quadratic.
not quadratic. We're not talking about a time-based. No, this is just a histogram.
Oh.
These are the histogram. It's almost like you have 2 subsamples. It's like you almost have 2 groups, right? Even though you have this one distribution, you have one that's not enjoying their job very much, one that is. So that's why there are a host of statistics based on classification. And we're going to talk briefly about that today in Chapter 7 with discriminant function analysis. Maybe you think you've got something like this, and maybe there's two subpopulations. So there's this whole area of statistics called latent class analysis, or actually they fall under called finite mixture analysis. And it's basically to find these unknown groups. To find these unknown groups that you didn't even know about. So maybe you think it's one sample, but guess what? There's really two homogeneous groups that are different from each other. And it's a really cool tool that I've actually got a couple people at USD to start using. They have multiple measures: depression, anxiety, somatization. And we actually did a mixture modeling. We found two really distinct groups: some that are high on depression, low on anxiety, etc., and another group that has different types of values on those variables. It's very similar to what's used often in marketing research called cluster analysis. Has anybody ever heard of cluster analysis? Anybody ever hear marketing term segmentation analysis? You ever give your zip code when you check out of a store?
Yeah.
Why? Why do they want your zip code?
To
know where they're-
different things in different areas.
Is there a chance that maybe just buying iPhones or electronics in the 92037 zip code in La Jolla might be different than Lakeside or Ramona or Chula Vista or Rancho Bernardo,
Yeah.
which has a big retirement community? So they get the zip code and they can kind of get an idea of certain segments. And that's why there are a host of really cool statistics that are geared for classification. In fact, Connie Dahlberg, Omar, and I, we co-wrote an article that came out the past year about some of these statistical tools that can be used for classification. So here, you may find if you have bimodal, transformations not going to help, but maybe there's two subpopulations. Homogeneity variance. You guys already know that well from the good old Levine, right? Again, the Levine, it compares groups on the difference from the mean, right? If you recall, it compares groups. That is, basically takes the absolute value, if you recall, of y, ij, minus yj. Where I equals individual, and j equals group. So it takes the individual score from the mean. Okay, pretend that's a mean right there, everybody. And individual from the group. And so it's a type of deviation score. It's a type of error variance. And again, as you recall from 6021, did we want the Levine to be significant or not significant? Yeah. So here we have two groups, 4.277, 4.277, the mean, male and female, and self-efficacy. Do you guys all know what self-efficacy is? You would have had that. What is self-efficacy? That's a variable often in IO psychology. Tell me what self-efficacy is.
You believe that you're able to do whatever it is you're going to do.
Can you be a little more specific? I mean, you're actually in the ballpark, but
So,
give me an example.
if you have a job
Okay?
and it's a little bit challenging, you still rise to the occasion and you're still confident that you can do it.
Why does confidence matter?
Morale, and it's shown that if so you don't give up, you have to be tenacious.
Do you think confidence matters in you being able to execute a job? If I'm a kid, throw up the ball and hit it, it's important that he or she feels confident they can hit the ball. Not that they will hit a home run. That's called outcome expectancies, right? That's different. Being able to execute the performance versus I want to hit a home run. But does confidence matter? And it does. And I've seen that variable sometimes be fairly strong in predictive modeling. So here, everybody, standard deviation is 0.76 and 0.80 between the two groups. Just on the surface, does that seem very different or not really? What?
Not really.
No, I agree with you. And here's the Levine from the one-way Nova. The p-value is 0.979. Happy or sad?
Happy.
Happy, right? It's definitely. So we failed to reject. And the null is that the error variances are what? Equal or unequal across groups?
Equal.
Equal, yes, that's the null. And what gives you, a lot of people think that the homogeneity variance is this, and they're not completely wrong. What is S square, everybody? What is S square, the notation for? The variance, right? The variance. They think the groups are equal. But technically, it's the error variance. Technically, it is an error variance, and this is what kind of gives it away. Levine's test of equality of error variances, which is parallel to which assumption in regression? Which is very parallel to the continuous variable. Yes, homoscedasticity. Right? It's parallel to homoscedasticity. You got it.
Yeah, isn't that distribution variant?
What, homoscedasticity?
Homoscedasticity, you're looking for equally distributed variance?
Okay, across, but instead of it being a fixed factor,
Oh, the residuals.
yes, it's the residuals, y minus predicted y, right?
Yeah.
And the mean of residuals is always what? 0. And here, if I have positive residuals, have I over or under predicted?
Under.
And if I have negative residuals, you got it. And here we would love the residuals to have a constancy of variance across all levels of x, or the predicted value, right? We would love it to be constant. So basically, it's the conditional probability of the error given x, right? When you think about homoscedasticity, it's the conditional probability of the error given the value on x, which is kind of like the Levine, except now it's a fixed factor. So, look if I do, let's say you say, I don't think Dale knows what he's talking about. I don't.
Never say that.
Well, yeah, but you might think it, Chad. So let's say I want to prove to you that it's error variance that the Levine ultimately tests. Well, I just created a little variable called the ABS, means absolute value. ABS, that's SPSS vernacular for absolute value. Self-efficacy minus the mean for males. For females, I like to take them to all the decimal places so I can make sure to get it perfect. And let's do you see all I did was took the score from the mean and the absolute value. And let's do a one-way Anova on that variable. And voila, everybody, surprise, surprise. The p-value is 0.979, same as Levine. So this shows you that the Levine tests error variance, right? An individual from what? Group mean or grand mean? Group mean. Right, each individual from their group mean.
Why would you take the absolute value if it's going to be 0? I mean, aren't you taking your...
No, an absolute value won't be.
But you're subtracting the variable by the mean, right?
From the mean, and then what it does is it doesn't make it have an average of 0, because the absolute value. Versus if I didn't have absolute value, then it would be 0. But taking the absolute value, guess what? Those negatives all become positives. All the negatives become positives.
Okay.
Right? So if I didn't have the ABS, you're absolutely right. The mean would be 0 for both groups. The mean would be 0, so the Nova would always have a
I was
p-value.
thinking an order operation, so you get 0,
Right.
you get the absolute value, but you're getting the absolute value of all the...
The absolute of each individual score, so it gets rid of all the negative values.
Okay.
Gets rid of all the negative values. Implications of violation of homogeneity of variance. If you have equal sample size across groups, you're generally going to be okay. Things get a little screwy when you have unequal. So here's some basic research that's been found. If you have unequal sample size, and the larger variance is with the larger group, it'll tend to be conservative. So if you have if the larger sample size has the larger variance, let's say you have more males than females, and there's more variability on depression, it'll tend to be conservative, which increases which error, everybody? Type 2. With unequal n and larger variance with a smaller group, right? With n equals 40, if you have the smaller group, you will have a liberal result, which means type 1. So think of it this way, everybody. I have 55 people in group 1, 40, and the larger variance is with a larger sample size. Does everybody see that? Which means the F will be conservative. If my larger variance is with a smaller sample size, it'll tend to be liberal. It'll tend to be liberal.
Why?
Why? Because one way to look at this, if I have larger variance, group number 1, group number 2, and it's got 50 people, it's got 30. Who's going to get more of a weight in the analysis? Who's going to get more of a weight, W-E-I-G-H-T, in the analysis? Group 1 or group 2?
Group 1.
Yep. And guess what? It's more spread out. So guess what? It's going to be harder to find significance.
Okay, got it.
So it tends to be a little bit more conservative.
Yeah, makes sense.
So, take-home message though. Things get a little bit screwy when you have unequal sample size. Unequal sample size. And there's no hard and fast rule. There are tables, and I even think the book shows some example of heterogeneous covariance matrices on page 229. Shows when things can get a little bit screwy. If sample sizes are relatively equal, you guys, if you got, sometimes people have emailed me when I'm on a project saying, I got 60 in one group, 50 in the other, is that a big problem? I go, not at all. Practically, it's not going to matter. What if you have 60 and 20 in the group? If the variances are equal, that may not be a problem. If the variances are unequal, then you got a problem.
What if you have two really large groups, like 4,000 and 3,000 or something? It doesn't matter.
I think that's a good question, because you could say relatively it's the same ratio as 40 to 30, right? Not that much. Like, let's say 4,000 to 2,000. Let's make it a 2 to 1. That sample sizes are so large then that you're not going to be impacted severely by any outliers in any respective group. So I'm not going to worry about that 2 to 1 ratio. I'll be more concerned if it's like 30 versus 15, because their outliers are going to have a distinct impact. 4,000 to 2,000, they'll pretty much meet the central limit theorem for both of those subsamples. So I'm not as concerned about that. Now, you guys, this is the real world. This is what I get not infrequently. I just did on a project last week. Caucasians, 35 Latinos, 25 Asian Americans, 5 African Americans, 3 Filipinos. You know, and I do get those, especially depends which hospital I'm at. The big difference is Sharp Chula Vista versus Sharp Coronado, obviously Sharp Grossmont, right? Very different ethnic groups. So what are you going to do? Because I guarantee you the variances are probably not going to be equal. Do you think outliers are going to have a bit of an impact on these two? So what do you do, everybody, if you want to do a one-way Anova? And you not only have unequal sample size.
Standardized?
What do you mean? Create a z-score? What would a z-score do?
Yeah, no.
What'd you do if you got this very real-world problem? 5 ethnic groups. You want to do a one-way Anova on ethnicity, and you have heterogeneous variances.
Yeah, don't you have to some way standardize
What do you mean by? Tell me how you standardize ethnicity.
not the ethnicity, but so you have 45 and you have 5. Isn't there some way to? No, I'm thinking out loud. I'm wrong.
Grouping those last two a little bit more.
You could maybe group them. It's not great, right? You could group them, or you may even group Caucasians, Latinos, and, depending, there's the ubiquitous other. It's not great,
Yeah.
but sometimes you may have to do that. Sometimes. When I'm on a study, and we've got 30 different types of cancers, which we did a few years ago, there were some small sample sizes for some were huge, right? Heart and lung cancer, but there were some specific cancers I never heard of before that had very small sample sizes. So I would defer to the oncologist. I said, we got 30 cancers, it's way too many to analyze. Can you think of a higher order categorization? And they came up, I think, like with heart and lung, brain, I forget, maybe something with renal, etc. So they came up with about 5 or 6 categories of cancers. So that's what I would defer to the experts if that ever happens. With categorical data, you want to do an Anova, you have really small sample sizes for some of these, and you don't want to just delete them. I mean, obviously you could do this. Right, I mean, you can delete them, but
You're losing information.
you're losing information, right? Because there's 5 African Americans, 3 Filipinos.
Fast
that
and
are-
loose.
What's that?
Fast and loose.
Right. So you might, and of course, I'm well aware that once you start to categorize, you lose that individual information. I know that clustering, Asian Americans, African Americans, and Filipino, you lose that information, and they're definitely not homogeneous. But sometimes you need to consider that for categorical data.
But even lumping Asian Americans in as Asian is, I mean, so you can make a case for it where I could even say, well, Filipinos are, Pacific Islanders. So
Yeah, but African American, you'd have a hard
Yeah.
time. It's absolutely
So
justified.
you're violating some of that independence anyway when you're saying all Caucasians are like.
Oh, there's a whole
I mean,
that's why the
that's a whole different
census,
story, but-
the census has 6 major types of ethnic groups that breaks it down to about 56.
Yeah.
All combinations, African American and Asian and this. It's become a nightmare for the census to try to analyze ethnicity.
Yeah.
Absolutely. I had one project where we had 25 different types of religions. I was working with a project at Fuller Theological Seminary. Religions I never heard about, like charismatic. One was called X, just had a big X. I mean, things I've never heard about before. I said, is there a way to categorize? And they ended up coming up with 5 really global categories. The ubiquitous other, non-denominational, Protestant and Methodist are large, aren't they? Pretty much so. It's other, non-denominational, Protestant, Methodist, and I don't know, with Catholic, Protestant Methodism are a form of Catholicism, right?
Yeah.
Offshoots.
Offshoots of those,
Yeah.
so I'm not sure what they did for the 5th one. I know they cluster Jewish, people, and everyone in the other. And so, it wasn't ideal, right? And so you're absolutely, to get at what you can say, you're going to lose that heterogeneity because they're probably not homogeneous. But those are some decisions I guarantee all of you are going to confront someday. When you want to do your ANOVAs, you see variances are radically different. Some of these categories have really small sample sizes. And what are you going to do that's going to make
I
sense?
would say, what would Dr. Glaser do?
Well, no, what will you do? I'll be long gone by then. So what will you do?
Where are you going?
Well, no, what I'm saying is I'm going to be around.
Tired on a beach.
So,
He's in the van down by
that
the,
doesn't sound
down
bad.
by the beach.
So, but I see a lot of articles that just kind of, they acknowledge it and then but say, well, we can't really do anything about it. How, is that okay if you just acknowledge it and say we can't really do anything about it as opposed to just...
Can't do anything about what?
Like whatever, like they might be violating something, some assumption or some sampling error. I mean, this is maybe a...
Well, sampling error just means how different the sample is from the population,
Yeah,
a biased parameter.
I mean, there's some issue with the survey.
Okay.
Or like with the study or a survey and they'll just...
Okay, let's say I
acknowledge
can't
it.
transform.
Yeah.
It's not normal, the transformations ain't gonna help, right?
Mhm.
But then there's options. There's non-parametric options. There's a whole area of robust statistics. So A, for non-normality, there's statistics that can handle that. Homogeneous variances, heterogeneous, nothing helps with that, right? There's statistics, whether it be non-parametrics or even statistical tools that have heterogeneous, consistent, they're called heteroskedastic consistent standard errors. There's actually standard errors that are equipped to handle heteroskedasticity.
So my question is, do you see a lot of articles that don't do enough to handle their issue, like handle
They
their
do, but a lot
issues?
journal articles, by definition, are not going to be near as detailed as your dissertations will be. Dissertations, you're going to have to address everything. Usually, you kind of assume by the time it's a journal article, they've taken care of the assumptions, but maybe not. That being said, sometimes they do address it. Sometimes they'll say a log transform was conducted, or given a violation of homogeneity variance, the Kruskal-Wallis, which is the analog to the Anova, was used. I always do. In my journal articles, the ones that I co-author, I always address it. And rarely there's always a method to be able to deal with some problem. Usually there is, whether it be missing data, whether it be heterogeneous variances, non-normality, there's usually pretty much options to deal with it. One may have to get a little creative and go to other software. One may have to use other software. You may not be able to use SPSS.
It just seems like now that I can read articles with a more critical eye, I see people not doing their due diligence for a lot
And that may be, or they just assume they've done all the assumptions is something you do. as a student, you address it. By the time you get to journal articles, we've assumed you've taken care of it.
Yeah.
But that may not be the case either. They may have just generally said, just ignored it. Like independence, you can't just ignore this violation of independence. People need to know about multi-level modeling, generalized estimating occasions, complex survey sampling, all of those which accommodate the violation of independence. So there really is a remedial action, an option for every type of violation. Yeah.
If we were to go on and take another statistics class beyond this, what would be the next, what would we get into?
Well, I'd love to have a course, devoted to structure equation modeling, multi-level modeling, and finite mixture modeling. That'd be my wish, because those are really statistical tools you will find that'll take you to the next level.
Why don't we do that?
They only have so much time in the,
You only have so much?
well, no, the curriculum went from 120 to 90
okay.
units, so there's a little less units. And people aren't as interested in the quantitative courses here. I did start an SEM course here in the 90s. And it had a little bit of interest, but it doesn't get enough interest. It gets 4 or 5 people, and
What if we combined with the clinical side? Could we got enough interest?
if you got enough interest, you guys.
Would you be willing to teach it?
Yeah, oh yeah, I'd love to.
Zach, you want to take that one?
I want to.
All right,
I'd love to, but you guys, that'll have to be your battle. That'll be your battle. But yeah, that'd be my next course. And then I would also have a course that's almost undergraduate-like, because there's a huge gap in non-parametric stats. All of a sudden, I mentioned Mann-Whitney, Wilcoxon-Sign-Ranks test. I mentioned the Kruskal-Wallis, the Friedman. Eyes just go blank.
Yeah,
Well,
no.
what the heck is that? Those are all parallels to t-tests and Anovas. No, and you won't. Undergraduate, I barely get chi-square in at San Diego State and USD. I might mention chi-square, so they get the 2 by 2. And then you go to graduate school, we take these Anova and regressions and fancy multivariate, and then all of a sudden, there's this whole area of non-parametric stats. These options that are available to you right under this here. Analyze non-parametric tests, all types, chi-square, binomial, 2 independent samples, multiple related samples, Kendall's coefficient of concordance. What do you have? Multiple people rating multiple individuals. It's called Kendall's coefficient of concordance. There's all these statistics. Even last week, I was working with a statistic that I don't see a lot. But I just did a report for a client last Friday. Analyze, descriptives, crosstabs. So let's say you have a 2 by 2. My outcome is stay on the job, don't stay on the job. Or it's just a relationship. I want to see if you stay or don't stay by male and female. There's even some options called lambda, or what's called the uncertainty coefficient. They're asymmetrical indices of what if that categorical variable is technically an outcome. And you're going to learn about it with Chapter 7 if it's an outcome. Not many people know about lambda, right there. Or what if you have ordinal variables, Summers D, gamma. So there's these whole areas of non-parametric stats that are equipped to handle ordinal level variables, nominal, ones that are even outcomes. And I just think we don't have time to teach it. So that would be something that I would also go over this whole
There's a
area.
couple classes we could eject for.
What?
I think there's a couple classes we could usurp and replace.
So, and I would think that going over the non-parametrics would be really, really, really helpful. And then I would get even into fancier stuff with what if you have mediators that are moderated or moderators that are mediated. I would get into some of these interesting statistical models that are regression-based, but using the process macro that's available on SPSS. That would help you to look at unconventional models that may happen in your dissertation. So what if you have something like this? You think the amount of workload you have impacts job satisfaction, impacts job performance, and maybe it's mediated. So here you have a mediator, because the relationship of workload and job performance is mediated by job sat. But you also think the relationship of job sat workload depends upon how much social support you have. You have a moderator and a mediator in the same model. So you can have a moderated mediator or a mediated moderator. So, and I would
Yeah,
also.
that's something we should be addressing as grad students.
Yeah. So.
I think.
But you know, the reality is, sometimes your dissertation may come onto things you weren't taught in class, and that's when you get to engage in what's called self-instruction.
There's this guy.
I had to do that a lot for my dissertation. You know, I had to do a lot of stuff. I mean, I learned a lot from my classes, but 95% since my classes I've learned on my own. You know, you get the book, you dummy up some data, and you practice. You use data straight from the book. You make sure you get the same results. And then for me, understanding the math has really helped me get a better understanding. I always do. You've never been in my office and make yourself, but I got a lot of papers on the wall, and a lot of it are just hand calculations. And to me, just because I understand it then. But I'm not.
There's not an inch of free wall space.
What's that?
There's not an inch of free wall space.
Yeah, it's pretty bad. So, that being said, everybody,
Thank you.
you're welcome. Now, the analog to the univariate assumption, which you learned actually in 6021, is, remember good old boxes, everybody? Remember when you had the simplest design was a 2x2 for a mixed Anova. Remind me what a mixed Anova is again? Remind me, we spent quite a bit of time on that in 6021. Tell me what a mixed Anova is. Do you want multiple choice?
Yeah.
A is a Dracula. B is that you have a between and within subject variable in the design. You have between and within, right? Remember?
Give an example.
Absolutely. Two groups are measured at two prairies over time. Right? We do that for a couple of homeworks there to take home.
Yeah.
Yes.
That's a mixed Anova.
That's a mixed Anova, right? You have males, you have females, you have a baseline, and you have a month 3 measure. And you're looking at organizational commitment over time between males and females. Or experimentally, right, an intervention group and a placebo. Maybe some meds. So here you have a 2x2. Does everyone see it's a 2x2
Yeah.
mixed Anova? What's my between subject variable? Which one is my? What's that?
Gender, males and females.
Oh, you're right. Yeah, gender or intervention versus placebo. And my within is
Time.
time one. So then you learned about the homogeneity variance covariance matrix back then. What's boxes M? So boxes M is the analog to univariate assumption for the multivariate design. For the multivariate design, everybody. And when you go into SPSS, when you go into analyze, general linear model, multivariate, options, you have just homogeneity test. It looks like the same interface really as Anova. And there's the homogeneity test for the Manova. Okay, so let's go ahead and do a Manova with all 6 DVs. This is a little bit on the busy side. Also, I don't know if any of you have availed yourself of the handouts that I've printed out. There's not only handouts, but also if you're at all interested, every single chapter I've appended a syntax file. I don't know if any of you have played around with it, but every chapter you'll see, chapter 6 Manova in class. I've got all these syntax files that you can play around with and do the results. I mean, do the analysis. Like here's the Manova. I mean, here's the Manova right there. And all of these, everybody, are on the syntax. Gets a little busy, isn't it? With 6 outcomes and 2 groups, it's a little busy to see if the variances are the same, aren't they? Right? How do I go from a variance, from a standard deviation? All I have to do is what? Square it, right? Standard deviation squared is variance. So you could square each of these, but it'd be hard to make sense of it. So here we have, let's say for now, we have 2 DVs and 2 groups. Let's say we have 2 dependent variables, everybody, and 2 groups. Which means you have 2 variance covariance matrices. What's on the diagonal? As you already know from the chapter we went over matrix algebra, we've gone over this in the correlation, 6022. What's that? The variance on the diagonal. Right, the variance is on the diagonal. The covariance. That's why you don't see it filled there because, right, it's perfectly symmetrical, so it's redundant. So here you have the variances and the covariances. That's what the homogeneity of variance covariance assumption tests. It tests the homogeneity of the variance covariance matrices. God bless you. Which means it can get pretty complex. Why? Think of, here we have, this is just the simplest 2 by 2, everybody. This is the simplest 2 by 2. Think if you have a 3 by 3. Think if you have a 3 by 3. Authoritarian manager, permissive manager, transformational manager. And you have 3 outcomes: job sat, job engagement, and job involvement. Which means you're going to have, does everybody see you'll have 3 variances on the diagonal? And you have the covariance of 2 and 1, the covariance of 3 and 1, the covariance of 3 and 2. Do you see we have 6 elements? Which means you got 6 elements here to equal 6 elements here, 6. And that's just a 3 by 3. Gets a little busy, doesn't it? So this means that the variance, remember, the diagonal is the variances, the off diagonal is the covariances, and you would love these matrices across the groups to be equal. And so it's the analog to which univariate assumption, everybody? It's the direct analog of which univariate assumption? Homogeneity of variance. You got it. You got it. So, that's tested by boxes M, everybody. And, as you may or may not recall from 6021, there's a statistical test. In accordance with homogeneity of variance, would we like to reject a null or fail to reject a null? Fail to reject. Would we like our P to be greater than 0.05 or less than 0.05? The P is 0.139. Happy or sad?
Happy.
Yep. There's the boxes M, 29.3. There's the transformation to an F with the 21 degrees of freedom. And that's it, everybody. Look at it here. It says test the null that the observed covariance matrix and the DVs are equal across groups. And that's homogeneity of variance covariance matrix.
I feel like it's something that got pushed into the end of the semester to do the whole wing debacle.
What's that?
I feel like that's something that got pushed at the end of the semester for us, for our cohort.
Yeah.
It doesn't sound, like when we remember we had to have that, like, that extra class after the class.
Oh, that was on the covariant. That was Ancova.
Was that Anova?
Yeah, Ancova got pushed. This one we were going to spend a bit of time on. This is the context of repeated measures and with a mixed Anova. That was not rushed. But yeah, the Ancova was because of less 1 week.
For some reason, this doesn't seem.
It doesn't resonate.
Yeah.
And well, you like 3 a.m. tonight, you'll wake up, Zach, and you'll just remember boxes M.
That's usually how it works.
It'll just, now,
Usually some screaming involved.
Yeah.
cold sweats, right? So, you may or may not be interested in the black box behind it, but boxes M is a function of sample size minus number of DVs and the logarithm of the variance covariance matrix. So you kind of want computers to do it, right? You have a logarithm of the determinant, right? Remember that means determinant of a variance covariance matrix, which we saw how to do with matrix algebra, minus the sum of where VI is n minus 1 degrees of freedom for each group times the logarithm of SI for each group. So you have the total sample size, then for each group. So it takes into account the variance covariance matrices for each group and does this nasty little formula. And if you recall, how do you get at a determinant, everybody? Right? We already went over that in chapter 2, right? If it's like this for males, this times that, right? Remember 12 times 15 minus 8 times 8. And 116, we can see the logarithm of 116 is 4.75, which would be the logarithm of the variance covariance matrix. Now, I'm not going to show this by longhand, but if any of you have any curiosity at the break to see the math, put on camera here, the math for how to exactly derive boxes M when you have a sample size of 10, 2 outcomes, 2 predictors, I got the entire math right here. So I'll just put it right up here if you want to look at it during the break.
Is it in your handwriting?
You
I'm
know,
just being realistic.
I've really watched, since I'm on camera, I've really kept what I want to say in check. So yes, it is in my handwriting. If the camera was off, I'd have another kind of a peppery little response.
Oh, you
But-
turn off the mic over there.
But when they get livery, then I'm really screwed. So yes, but you'll find it's actually pretty legible, Smarty Pants. So it's right there. So if you're interested, I used to draw that out for the class. I used to show it, and they just fall asleep. So I've cut a lot of the math from what it used to be in the class, but I just want to show it to you where the black box behind box was in. Now, so we failed to reject the null of homogeneous variances, right? So you can see that boxes M is based in part on the determinant, which brings us back to matrix algebra. But it's also very sensitive to multivariate normality violation. Which means if it is significant, everybody, you probably either A, don't have to worry about it much, or that maybe it's more non-normality than radically different variance-covariance matrices. So, that being said, everybody, I think the book even says, right, if the box's TEM had been significant and the larger variance was with the larger group size, then it would be conservative. In that case, we would not be concerned, for we would have found significance and even more stringent. So if it's more conservative, why is that kind of a good thing? Because then you're keeping in check what error. If it's more conservative, because the what type 1, you're keeping in check type 1. Exactly. Again, it depends what you think is worse, false positive versus false negative. Now, what would have been concerned is if the large variances with the large group size and group effect was not significant, then it would be clear what the reason is for that. So the book does talk about transformations, and that's a possibility. But I'll tell you where things get screwy with transformations, you guys. You can do transformations, and maybe that'll help. Let's say this is the culprit. Let's say job involvement is the culprit. Right? Job satisfaction looks pretty good. Job engagement looks pretty good. All of a sudden you do a square root transform. So the mean for this group is 26. The mean for this variable is 28. The mean for this one is 4. Because I've done a square root. So statistically, it won't have a huge thing in terms of the F values, but the descriptive stats get a little screwy, don't they? The descriptive stats. So it's always weird to transform just one or two of the variables in a Manova context. That being said, this is a very restrictive assumption that also is impacted by multivariate non-normality, which means you may not always be certain if boxes M of P 0.03 is due to differences in the variance and covariance matrix or non-normal distributions. Again, the text does point to transformations as one option in the event of a reject the null, and that is one option. That being said, there are also other statistical tools. That can handle sometimes these lack of homogeneous distributions. You also get this other test called Bartlett's test of sphericity. The Bartlett's test of sphericity, if the test the null hypotheses that the residual covariance matrix is proportional to an identity matrix. Wow, that's a lot of complex words. Do you guys remember what an identity matrix was? 1 on the diagonals, zeros. You would have been introduced to that in repeated measures when you learned about sphericity. Because sphericity ultimately tests against this identity matrix, where we assume the residuals are uncorrelated, or the difference, time 2 minus time 1. Time 3 minus time 2. The difference variables are uncorrelated. So what we want here is, if the determinant is close to 0, one or more variables are almost linear functions of the other IDs. So let's say you have the first ID is leadership decision making, and the other is leadership locus control, and the third is leadership problem solving. Do you think those are going to be correlated? the 3 DVs? So let's say the average correlation is 0.85. With Manova, which I'm not going to hold you responsible for, you can look at the Bartlett test and see if it's significant. Because remember, we don't want them too high. You want the DVs to have some correlation, but not too high.
So since they violated that, we would say,
Well, it's not as much violated per se. This isn't necessarily, it is kind of an assumption, but what we want to say is, are they too highly related? You may want to examine the correlations of the DVs. Now, what I want to show you, a little detour with a Manova language. In repeated measures in Nova, you definitely will have to know about sphericity. With Manova, I'm not going to have you worry about this. It's nice to have, when we get to repeated measures, absolutely. Let's say I run the Manova, everybody, with the same DVs. Same DVs. Exercise, diet, and sex, male and female. And you can see here, look what you get, everybody. You get all the univariate homogeneity variances. Right? You see all the assumptions, everybody? You get for every outcome, you get the p-values. And we see we don't have significance for any of them. Exercise, diet, health. So that's a good thing. And then, for each cell, everybody, for each group in Manova, for each group, you get the correlation matrix. And you can get an idea of how highly related the DVs are for each group. So you see, exercise and diet have a 0.5 correlation. Self-efficacy and self-confidence, 0.45. On the diagonal are the standard deviations. And look what it takes, everybody. The determinant, 0.044. That's used for boxes M. That determinant of the covariance matrix. And then you take the log of the determinant. So you see where matrix algebra rears its ugly little head in a Manova. Then we pool these together. If I have 2 groups, I'm going to pool 2 variance covariance matrices together. And it pools, that's called within cells, all the variance covariance matrices. And look, it does a determinant of the pooled covariance matrix. Negative 3.22, used for boxes M. So it pools them together, everybody. And here's boxes M, everybody. Same result. P-value of 0.139, there's boxes M. So I just want to show you, in the Manova, you can see that it takes a determinant for each group, then for all of those, and that's how it gets at homogeneity of variance covariance matrices. Again, everybody, we've gone over the multiple tests of significance. For our class, I'll be fine using Wilks Lambda. They all do have separate types of properties, contingent on how many groups, how many DVs. But here, if you have the simplest design, they'll all be exactly the same. So here, everybody, the p-value is 0.74. Reject or fail to reject. Remember, it's comparing males and females on the linear combination of exercise, diet, health. Reject or fail to reject with a p-value of 0.74. What's that?
fail.
Failed to reject. The effect size is 0.025. That's the multivariate effect size. 2.5% of the variability in the linear combination of the outcomes is due to between group differences. Does everybody have that? 2.5%. So as we see above, and you can always report the F to everybody. F with the degrees of freedom, hypothesis is 6,139. We saw last week how they calculate that. Equals 0.593. P equals 0.735. And eta squared. Here. There we go. .025, which means there is not a significant between group difference on the linear combination. I know I'd be redundant when I say that, but linear combination means, right, that we've got these 6 DVs simultaneously. Look at the 6 outcomes. And again, same as the Manova, there's the Levine test for each of these. So look at the univariate stuff, everybody. Look at the univariate and the multivariate assumptions. And if you do have significance, you can then drill down to see if you have any significance for the univariate, which is just the one-way Novas. Now what gets tricky is someone says, if I don't have a significant Manova, can I just look at the univariates? I mean, technically, it's just like running 6 different Anovas. It's using an error term that's unique to each one. So I guarantee you this is the same as we saw last week as running a one-way Nova. So there is a little bit of a problem of which error rate. Which error rate might be slightly inflated. So you know what, I don't have significance from the Manova. I'm just going to go ahead and look at each of the 6 Anovas. Which error rate might be slightly inflated? Type 1. So you might, if you want to be conservative, you might want to employ a lower type of alpha, right? Maybe a per comparison. Maybe just to be a little more conservative in the event the Manova is not significant. So again, the Manova assumptions checklist. Assess independence of observations. In other words, part of that is just your knowledge of your sample, your knowledge of your sampling. If you have 25 classrooms of kids, and you have 5,000 kids, is your sample size 25 or 5,000? 5,000 is individuals, 25 is classes. But there's a problem. Is there a chance that kids within a classroom might share some attributes that creates homogeneity within a class and heterogeneity between?
Yes.
In my era, it's probably, I don't know how different it is now, but in my era in the 60s, if you were in Mrs. Quinoz's class in 5th grade, you were kind of in the smartest. If you had Mrs. Torrio, you were medium. If you had Mr. Garrison, you were challenged. And all the kids were not that sensitive about which class you were going into the next year. You're going to Mr. Garrison, you're in the dumb class. And so, that being said, could there be homogeneity within classes and heterogeneity between? So if I clustered those 90 kids together, pretending it's one universal pool, guess which assumption I'm really violating? Independence, right? So that's why now there's no excuse not to take into account the violation of independence. You asked earlier, do people sometimes ignore that stuff? Yes, I've reviewed a couple journal articles where even they might acknowledge there be non-independence, but we went ahead and analyzed it as if one sample. And I come back at them and say, the fact is you have 12 different countries there. Could there be certain things unique to countries when you're measuring political conviction that's very different? That there's inter-country variability that you will not be able to find. So now we already know there are statistical tools that are well equipped to handle this type of violation. And we've gone over that in class. And I know Bernardo has a big data set right now that he's working through. He has multiple countries. He's got a large data set, and there's multiple countries. It's absolutely perfect for being able to do multi-level modeling, or some people call it hierarchical linear modeling, or generalized estimating equations. Statistical tools that can handle that. Assess both multivariate and univariate normality. Assess univariate homogeneity variance and homogeneity of variance covariance matrices, right? Via boxes M. If box M violated and you have large group size and approximately equal, you're okay. But if unequal N, if larger variance with large group, the test will be conservative. If larger variance with smaller, it'll be liberal. So you may want to consider some types of variance stabilizing transformation. Or adjust your alpha. There's no real magic trick out there, everybody, for violation of homogeneity variance covariance matrix. There's no real non-parametric analog to the Manova out there that doesn't care as much about that assumption. So again, you might want to have a lower alpha if the large generalized variance is with a small group size, right? The large generalized is the determinant. If the large variance is with a small group size, you might want to lower your alpha. Whereas if the large variance is with a large group size, higher alpha. So, that being said, everybody, that being said, that goes over a lot of assumptions that are very, 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 very similar.
I have a question about the homework. I
Yes.
started it and I was a little confused because the fixed factor is sex,
Okay.
but then aren't the three groups, excuse me, the three groups fixed factors as well?
Yeah, but I haven't assigned the homework yet.
Oh, I thought you said go ahead and start it.
Did I assign the group? Did I say?
Last
Oh,
week.
no, I created the 3 groups, right?
Yeah, last week you
Oh,
said
last.
start it,
Right.
and
Okay,
so I
so-
did that. but then
Okay,
I
hold on.
didn't-
This is old notes, and I just created that last week, didn't I? There's okay, oh, for the homework. Hang on, you guys. Yeah, I did create, and I put it on Moodle right away, didn't I?
Yeah,
Right.
I think I did. Hang on, let's look. I know I did it right. Literally 5 minutes. There I did. Employees recap. There we go. Okay, let me go ahead and replace some of this here. There we go. Okay, here. Oh, I already put in the notes. Full-time, part-time, others. Sample sizes aren't perfect, are they, you guys? 74, 26, 51. But that's not unusual. Last week I was analyzing a variable for nursing, full-time versus part-time versus per diem. You guys ever heard the term per diem? Paid by day, radically different sample sizes. We'll use the same DVs. Psych, well-being, health, social support. So run a one-way Manova and also run the post-hoc. Go ahead and use the Tukey, everybody, and interpret. If you desire, you may want to run one of the comparisons and the contrast options, just for fun, right? If you want to run a certain comparison. Or use the special syntax as per notes. But yeah, it was not due till next week.
so sex is the fixed factor?
No, this is the fixed factor.
I'll go up.
Full-time, part-time, others.
Yeah, go up a bit. Because it says as fixed factor sex.
Okay, that's just because it's left over. from somewhere.
Okay,
That's just left over somehow.
thank
Here
you.
it's got like a table here. There you go.
Okay.
Nope, this is the fixed factor. And I did that right at the end last week.
Thank you.
So you guys, you're going to run the full Manova, compare the 3 groups, run the post-hoc, discuss the assumptions, and hand that in next week. Questions on this one? Yes, sir.
What 5th grade class were you in?
What's that?
What 5th grade class were you in?
Oh, I would never say so. I will not relive.
Something tells me it was Mr. Garrison's.
Not that Mrs. Kenyasa smarty pants. So, okay, guys, that is that for chapter 6. And of course, I don't know if you guys are at all reading this book, but the reason I did is it's got very nice user-friendly chapters to each of these. So the Manova is just a nice supplement, and this is, and I may ask a question or two from the test. So this is on page 245, everybody. And again, does a really nice user-friendly job on Manova. So the purpose of Manova, homogeneity, variance, independence, everything we've gone over in class actually is in this book, except Mankova and repeated measures Manova. Okay, we'll talk about that later on. So, any questions before we move on to chapter 7? I do want to say the appendix in your book on chapter 6 has a whole section on correlated observations when you violate independence. And it does bring up using hierarchical linear modeling, multi-level modeling. It does bring up that as an option. So it does discuss exactly that. Let's move on to chapter 7, everybody. Let's move on to chapter 7. Any questions about Manova? Any questions? Do you mind if I run one really quick, just to make sure you know how to interpret it? Okay, let's
That's
just.
fun.
Well, alrighty. And so let's go and run, because I really want to make sure, because you get a blizzard of output. And I think sometimes people get a little confused what exactly they're going to analyze. So I'm going to take Let me see which variables. God bless you. So analyze general linear model, multivariate. This is, I'd like us to do a post hoc, but I'm just going to put in sex just for, or do you smoke? Yes or no? Let's go ahead. And even though I would usually not do individual items, I'm going to put in 3 items about exercise. Sometimes people have said, I've seen this on the statistical listservs, they said, what if I want to do a Manova and each outcome is an individual item, not a scale, and let me go and do this for you really quick here. What if my DVs are like this? What if they're individual items? Does everybody see exercise is something I plan into my weekly schedule? Working out on a regular basis is important to me. I often exercise to maintain or control my weight. Do you see it's just 6-point items?
Yeah.
Do you think each of these are going to have perfectly normal distributions?
No,
Why not?
because they typically don't.
Okay. Not bad for individual items, but the fact is, sometimes people say, can I do a Manova on individual Likert items? And that has come up. Yeah, you can do the Manova. We always say, sure, you can. I mean, the computer's not going to stop you. Whether it's going to meet the assumptions, whether it's appropriate, it's hard to say, everybody. I do know the research has shown, once you have 5 or more, and there's quite a few articles that show 5 or more scale points, right, from strongly agreed to discrete, it tends to do okay. It tends to almost approximate it as if the outcome is linear. So if your desire is to look at 3 individual customer satisfaction items, not scales, but items, you're kind of pushing it with Manova, but it might be okay. It might be okay. Are there non-parametric analogs to Manova? I have no idea. There probably is out there. I'm sure someone's created a macro out there that's a non-parametric analog to the Manova. Because there is for the Anova. What is it for the Anova, you guys? Do we know what the non-parametric analog to the one-way Anova is called? Anybody?
Dracula.
Okay, so let's put an ethnic group here. And let's put in age here. Let's say I have 3 groups, African American, Latino, and Middle Eastern. It's called the Kruskal-Wallis. The Kruskal-Wallis converts each of the scores into a rank. It converts it to a rank. So essentially, a lot of these non-parametric stats do that. And I know we've gone over this in 602.1 when we introduced the Kruskal-Wallis briefly as an analog to one-way Anova. Let's say I have a score of 1, 2, 6, 9, 18. Is there an outlier there? 1, 2, 3, 4, 5. There's the rank. Converts it to a rank. It does a difference in the ranks. That's the Kruskal-Wallis, which it really doesn't have any of these underlying assumptions about homogeneity of variance, normality. I use these a lot in my healthcare consulting. A lot. And here you can see, now you get the Kruskal-Wallis, which is a chi-square type of statistic. I don't know of one similar for a Manova. So this is parallel to the Anova. It's the analog to Anova. I'm sure there's a non-parametric analog to a Manova, but it's not embedded in SPSS. I'm thinking that I could do this in one of my other softwares. Or, yeah, in fact, I know in some of my structure equation modeling, I can do a non-parametric analog using the proper estimator. Otherwise, I was thinking, now that I'm thinking aloud, you could probably finagle this. Using generalized linear modeling, have the multiple DVs. See, the thing is, it's still going to want DV. But what's nice about it is, I bet there's a way you can do this using mixed models. And look what we have here. Just let me give you an example, just for generalized estimating equations. The response variable type of model. I would hit ordinal logistic right there. Ordinal logistic, but it's going to think that there's only one outcome. But I bet there's a way of taking generalized estimating equations with multiple outcomes and using the log-link function. So I'm sure there's a way of navigating the software. Because for one outcome, it'll work perfect. For one outcome, this will work perfect. I'm thinking for multiple outcomes. There might be a way of doing it.
What happened to going over to Manova?
What's that? We are, but I just want to show you.
Ah,
What if it's
okay.
individual items?
Okay.
What if it's Likert items?
Oh, that's where we got to this.
Yes,
That's right.
yes. You on track there, kid?
Yeah.
So,
It's early.
if you have a Manova with individual items, you guys, I'm sure some out there has created some type of macro to be able to navigate it. And I know in structure equation modeling software they have. Within SPSS, I think if you have 5 or more scale points, it might be okay. So let's run the Manova on these individual items. First, always look at the means and the standard deviations, get a feel for the means. We can see for exercises something I plan on my weekly schedule. Obviously, sample sizes are radically disparate. Because do people tend to smoke or not? No, right, exactly. Most people do not smoke. 115 people do not smoke, 28 do. So here you see for all 3 of these DVs, you have a higher mean for those that are non-smokers. Is it a shock that non-smokers often exercise to maintain or control their weight, working out is important, etc.? So we all have higher means. Boxes M, everybody. Let's look first at the univariate test, homogeneity variance. Happy or sad? Each of those have p-values greater than 0.05.
Happy.
Yep. And now let's look at boxes M. Boxes M has a p-value of 0.635. Right. We have failed to reject the null being that the variance covariance matrices are equal across these 2 groups, smokers versus non-smokers. Here's your Manova. For now, just focus on Wilks lambda. Reject or failed reject? Reject. Does everybody see why we reject the null? What's the p-value, Ross? 0.05. And the multivariate effect size is 0.088. 8.8% of the variance is attributable to smoker versus non-smoker on the linear combination of those 3 items. Yes?
In the other book that we read, the G and Y book,
Uh-huh.
it talks about hotelling's T,
Yeah, we showed the math for hotellings.
lambda.
You were not here. You
Oh, sorry. But is that,
okay too?
you want us to look at the lambda?
They're both pretty much the same. They're both pretty much going to be the same. The hotels, as I showed actually in class, the math is a little different. It's the generalization of the T test, and I actually showed that.
Yeah.
But hotelling's trace, especially when you have similar design, they're both going to be exactly the same. For now, we'll do Wilks lambda. The only reason, there's no hard and fast rules. Some have better properties, especially with certain, not only sample size difference between groups, but the number of DVs. Once you get multiple DVs, sometimes they can vary a little bit.
Okay.
But here, Jonathan, they're exactly the same. What's nice about Wilks lambda, it's the inverse of what? Wilks lambda is the inverse of, I know you guys know, it's on the tip of your tongue. This could be a good test question.
Yeah.
Wilks lambda, everybody, is a function of
The discriminant? Error divided by.
error divided by total. So it's the inverse of the effect size. Right? And look right here, 0.912 plus 0.088 is 1.0. Right? 0.912 plus 0.08 is there. So that's what's kind of nice about Wilks lambda. And one reason why I have you do Wilks lambda is that the way it can break down variability.
So you would say 1 minus Wilks lambda.
Would equal partial A
Effect
squared.
size.
You missed a really good lecture.
I watched it, but it takes a
Okay.
couple times for it to, I get the aha moments.
And you have the aha is
I go, oh, I get it.
excellent. Chad says the same thing usually about 3:30 a.m. Right, Chad?
That's my edited version when the camera's on.
Yeah. Okay, guys, the Manova is significant. Then what? So now you have the linear combination of the outcomes in these three items manifests significant between group differences on smokers versus non-smokers. Then what are you going to look at?
Individual items.
The Anovas. You got it. Do you have to do any corrections, Zach? No, not really.
And Tukey tells us what? If it's violated. No, Tukey's post.
And does post hoc make sense for two groups?
No.
Right. It's only going to make sense for
That's a repeated.
three or more groups. The two keys going to be the same as the Anova. Let me show you. Let's say Dale, again, I think you don't know what you're talking about. So I'm going to do analyze,
Oh, no, I usually don't.
multivariate, post hoc. You're going to put in your little two key right there. Okay? How about that little error message?
Yeah, I've gotten that.
Yeah, sure. Post hoc, not for because there's fewer than three groups.
Yeah, got.
There you go. So how are we doing with the Anovas, everybody? So for the item, exercise something I plan on my weekly schedule, the P is 0.12. Fail to reject or reject? Fail to reject. 0.001 and 0.028 respectively. For working out, it's important to me, I often exercise. Reject or fail to reject?
Reject.
Reject. So we got significance on two of the items. So does this show you, A, I can have significance on Manova, but it doesn't mean I have significance on all my outcomes. On all my outcomes. So there you go, everybody. It looks like the last two items is where you see significance. And no surprise, larger effect sizes. Larger effect sizes. And so that pretty much really gets at a lot of the Manova. And of course you could do contrasts, you could do fancier things if you wanted, but for now you just have two groups and this will be fine. For your homework though, you do have three groups. So you can, once again there indeed you'll do the Tukey. And one option I do want to state, everybody, one option, and I want to put this in the notes really quick here. I want to add this to the notes. Note, if the homogeneity of variance as I'm learning to type, assumption is not tenable, consider using Games How for post hoc test. Analyze, general linear model, multivariate, post hoc, Games How, right there. Games How. Do you see where it says equal variance is not assumed? The games HAL has some really nice properties. And the research has shown if equal variance is not assumed. So you may want to consider it. I mean, you could do both the Tukey and the games HAL and see if they're very different. See if they're different. So that is an option, and I do use the games HAL for my healthcare consulting when you don't have equal variances. In lieu of a transformation, I'll use the games HAL. That's got some nice properties. I know we talked about that in 602.1, but I just want to make sure that you know that that's an option for your homework. Any questions then, everybody? Any questions? Okay, cool. Let's take 15, 10:26, come back at about 10:41. And we will start on chapter 7.